have been hearing about the wonders of machine learning approaches, I'd like you to think a bit about quantum technologies, and that's what I would be focusing on. So, in particular, I'm going to talk about cross-architecture tuning of quantum devices faster than human experts. What I mean by this is that we can develop machine learning approaches that are that can be applied to different types of quantum devices and can achieve more things than we can in this setting. So actually, the motivation is that we are working very, very hard to develop quantum devices that would enable us to innovate in terms of technologies with new quantum clocks, sensors, simulators, quantum internet, and I'm sure you have heard of quantum computing. Now, there are some challenges in this development, and one of the challenges is that we need very complex quantum circuits. And as I said, we are working hard, but we have to be able to tackle those challenges. And alongside, there is machine learning and breakthroughs that are giving us hope that we can basically use and develop these approaches in a way that they are bespoke for quantum technologies. And that's what my group has been focusing on, and I must say that it was quite impressive what we could achieve. But before I can tell you more about that, let me tell you a bit more about what is the issue with quantum devices, okay? So, classical bits that we are all very familiar with, they can be just 0 or 1, right? That's the way we encode the information. And this is great because we can encode these in classical chips very easily with transistors in which we have gates that basically control the current on or off. And in that way, we have zeros or 1, okay? So far, so good. Now, quantum bits are a bit more complicated, and the reason is that not only do we have space to compute in which we have zeros and ones, but we have combinations of zeros and 1 in a way that it maps a sphere that we call a Bloch sphere, okay? Now, it's not so easy to encode these qubits in a physical realization. Actually, there are different types of quantum chips in which these qubits, that, as we call them, can be encoded. So some of these approaches are semiconductors, some are superconductors. There are also ion traps, NV centers. So there are many physical realizations, and we are all pushing very hard to make those work. And they do, and in small kind of bunches. And the reason why more complex quantum circuits have not been developed yet, it's because we not just have a gate that controls current on and off. We have a lot more gates, and the tricky point here is that the environment also controls these quantum states. So we have to be constantly aware that because these quantum bits are very sensitive to the environment, they are very good sensors, they are also very, very hard to control. Yeah? So it's a control problem that it's, well, in my opinion, very interesting. So how do we do it now? Well, we have these different quantum chips, and we have our humans that sit down and grab one of these chips and starts performing different tasks to encode our qubit. Once we encode these quantum states, it's not that the tasks of the human stop. Then we need to optimize the operation of such qubit. Okay, and this is like a sequence of tasks. Now, why is this a sequence of tasks tricky? Well, it's a big parameter space. Again, we just don't We don't just have a gate that controls on and off, but many gates and many control parameters. Also, we have big variability between devices. What does this mean? Well, a small, tiny difference in fabrication between one device and another will make a difference, okay? And therefore, we cannot just write a script that says, oh, please tune my quantum device, and it will work, because they just have different characteristics. So they are very good sensors, but again, one atom out of place, and your qubit would be able to know, okay? And also, we have to be very precise, again, because these quantum states are quite fragile. We have very narrow error thresholds, error margins, I mean. Okay, so how is a quantum device lab? So here you can see, for example, mine at Oxford. You can see our quantum hardware. In particular, we have a chip that is cooled down to below 20 millikelvin. This is a 20th of a degree above the absolute zero, so very, very cool. And humans here are basically sending signals that go all the way down to these very low temperatures. And then same humans, check the signal, see what comes back and what needs to be done, make a decision, and until they are happy, this is what happens. And this happens in different physics realization, being semiconductors, superconductor, ion traps. Actually, for superconducting qubits, there are these directed acyclic graphs in which there is an order of tasks that goes from the basic tune-up to the more careful tune-up of these devices. So you can see that actually, this task of tuning and characterization is quite hard, time-consuming. And well, actually, here, just to show you how these signals get to the chip, you can see inside our dilution refrigerator, this is not a quantum computer, but the dilution fridge that cools down our chips. And you can see that in the coldest part, here at the bottom, we have our chip, which receives the signals and outputs signals that are seen by spectrum analyzers, for example. So this is the type of data and the type of experiments we deal with. Now, as I was saying, the goal is to make complex quantum circuits. Why? Because those are necessary to do complex tasks and to surpass the current capabilities of classical technologies. So, for example, in superconducting devices, there have been in the order of 100 qubit devices put together. There are ion traps, also semiconductor devices, and all of them are in the process of scaling up. We need more and more and more of these devices all together, tuned, characterized, and working to their optimal conditions. So that's our challenge. Now your next question is, why do you need so many to make something useful happen? Well, the reason is, again, that quantum states are fragile. So what we need, it's a lot of physical qubits, let's say physical devices, in order to make them operate, or make a bunch of them operate as a logical qubit. So we need some sort of control layer that makes these physical qubits as logical qubits, in which we can run some sort of quantum software, okay? So basically, many of these qubits are acting as ancillaries to cope with errors, okay? So that's why we need so many, because we have devices that make errors, and the more errors they make, the more physical qubits you need in order to computation. Okay? If our qubits would be perfect, then we wouldn't need so many. So there is a balance there. So what is this control layer? Well, this control layer, it's this process of first encoding the qubit, then optimizing the qubit, and stabilizing it. Okay? And currently, it's done by humans. What my group has been focusing on is replacing humans here and introducing machine learning approaches to deal with this so that we can actually scale up these technologies. This is not easy, and you've heard a bit already about the problems with small data sets. Our data sets are measurements that we take at 20 millikelvin. They're expensive, time-consuming. So we are in the order of, well, maybe not 10 and 20, but 100,000 probably. So that's the range we work in. And again, we have big variability between devices. We have the problem as well of very flat optimization landscapes. Sometimes our device just works in a very small portion of the parameter space, and that makes our optimization quite hard. Now, also we have to deal with noisy data and in some cases hysteretic data. So there's a bunch of problems that make this machine learning challenge very interesting. So, in particular, in my lab, we focus on semiconductor devices, okay? So, what I'm going to tell you today is how far we got at actually applying these techniques in semiconductor devices. But what I hope today is that you can see in what we have achieved many similar problems that are not on quantum devices, but that are similar in terms of what has to be solved, and that many of our approaches might be useful for completely different types of research. So, in particular, you can think of our chips as very, again, as very simple circuits in which we have gate voltages that control, for example, 2 electrons and a bias voltage, and the only thing we can measure is the current. Not true, we can measure other things, but let's stay there. And then we will encode our qubit basically into in a block sphere in which we have either the electrons with spin parallel or anti-parallel. Basically, to achieve that, it's not easy, but let me show you here a micrograph of these devices. They are 500 nanometers. This is the scale bar here. And the gate voltages are applied to these electrodes that you can see below. So these are our devices that we cool down at very low temperatures. Now, how do we encode a qubit? Well, there are many measurements that humans require, at least to make sure we are on the right path. And, well, the question is which type of measurements the machine requires, and which of these measurements actually are needed and which are not. Some of these, follow some kind of tradition, just because I've been taught as a PhD student that I have to, do this measurement and this other, but then you realize that are actually not that necessary, and which is actually the crucial information. So in particular, we divided this problem in different steps. So the first step was to trap the pair of electrons, then characterize the electrostatic environment of these electrons, and finally refine this environment and find the optimal control frequency of that qubit. But you can see that the types of measurements we use are quite different. Well, they look quite different, but they are patterns that, are quite clear. So we have current as a function of gate voltages and frequency and time. Well, we have this pattern that we as humans kind of study in sequence to say that we are actually encoding these qubits. So far, separating these steps, we have managed to go quite a long way. And this is, I'm focusing, of course, there is work from other groups. I'm just focusing on mine. But we went from step 1 to step 5, and now we are pushing into the optimization of qubits. Some of these approaches that I show you here in this different work that my group has gone through uses deep learning, and some not so much, and there are some hybrid approaches. Now, the reason is exactly that of the small data sets that we have to deal with. So you can see that in step 1, where we have a device that we have no idea which parameters it requires, then we can't use deep learning. There is not enough data. But as we narrow down the parameter space, we can introduce more and more these deep techniques. Okay? So of course, I'm not going to torture you with absolutely all these kind of different approaches that we use. I'm going to pick one, and I hope you like it. And then if you're interested in other approaches, we can talk afterwards. So in particular, I'm going to talk about one approach that doesn't use deep learning, and is the first stage, the trapping of the electrons. So let's go to step one. So basically what we have when we have a device that has never been measured before and it's new in low temperatures, we have that for some gate voltages, there is a lot of current flowing. That would be the normal transistor being on. Or we have absolute no current flowing. That would be the transistor being off. But we are interested in is in the quantum behavior. So we are interested in this, small kind of parameter, part of the parameter space where there are features. And those features tells us that we are on the right path, okay? So we have to find these features. And here it's quite easy because it's a 2D plot. And we say, well, we find the lines. There is not much to do. Now, the thing is that devices have different gate voltages that control these states. And just because you want to control the parameters or because you want to make these gate voltages control the coupling between different devices, we find ourselves in a 3D space. What you can see here is a modeling of the basically the hypersurface defined, or the surface defined between the current and no current areas of parameter space. And we know features would be around that particular surface. Now, as we grow in dimensions, well, things get more complicated, of course. Well, here we spent a long amount of time. We never has done this before, just because it's insane, really, to spend months measuring in 3 dimensions this surface. And you can see that it's a surface that it's quite, it has lots of features, and it's difficult to optimize them. So now, this is 3 dimensions. Most of the times we deal with 8. So you can see, looking for these features in an 8-parameter space, in an 8-dimensional parameter space is big. So just quickly, because I don't have much time, we can do a back-of-the-envelope calculation together. But if we have 4 gate voltages, we have in the order of 4 times 10 to the 12 points to navigate, because we look for features in the millivolts range. And at the typical speeds we measure, that would keep us measuring 127 years. Not great, okay? That's not the way we do it. But the way we solve this problem was basically, and I'm going to rush a bit because I don't have much time, but we can look at it later on, is to have the algorithms perform observations in real time. And it doesn't know this surface. But with initial observations, we can use a Gaussian process to make a model of how this surface might look like. And we are able to choose more promising locations. Then we can investigate those locations. Investigate those locations by performing further measurements. And we feed back that information to our Gaussian process. So in this way, we are able to basically tune our devices, find these features a lot quicker. If we do it randomly, it takes more than 9 hours. Human experts take more than 3 hours. And our algorithms, the latest runs are less than 10 minutes. Let me show you now. We have done this in completely different types of semiconductor devices, and that's why I started the talk talking about cross-architecture, because actually the algorithms do not care too much about how your semiconductor device looks like, as long as it has this surface that divides different states. Okay, so I think I'm done. Just to show you our latest work that we are very proud of, in which we are basically introducing models, physics models to our machine learning models in order to tune quicker. But I will just flash through. And well, this is to say that we connect to different labs around the world to tune and characterize their devices as well. So our approach is being quite successful. And okay, in this way, just to tell you that all we want to do is find new ways of computing, and machine learning is allowing us, and hopefully it will allow us to do so. So thank you very much.
Thank you very much.